Hello, this is Dr. Keith Schubert, and this is a video lecture on how to handle second-order differential equations for circuits using phasors. So we're dealing with steady state in this particular case. So what's easiest to do for these, we'll start off with a simple little example here, or actually just do a simple little example. Let's consider a circuit in which we've got a sinusoidal current source, and we will have a capacitor here. Let's say initially we'll just call it C, and we'll stick a resistor that's R, and we'll take our output across an inductor, which we'll just label as L, so keep it nice and generic. And this is our V out, and this, since it's a current source, is our I sub S. And we will consider this our ground, and we will consider this point here our voltage for the source, and of course this is voltage for the output. Alright, so this is kind of our setup on this. In addition, we'll make some basic assumptions. When we're dealing with steady state and I've got a sinusoidal forcing, when we're doing phasors, we should specify what frequency we're working at. So we're going to pick omega is equal to, let's say, 10 to the fourth, and that's in radians per second. So we will then pick, let's see, we got C and an L and an R, which we'll pick this to be, let's say C to be 1.1 times 10 to the fourth, and that's farads, of course. And L we will have to be 1 times 10 to the, actually let's make this 10 to the minus third. That's a pretty big capacitor that I wrote there. I think I just copied that down. Let's see, let's say 10 to the minus fourth henries. And let's make the resistance, we're going to pick this one to be fairly small, and I'm picking this in particular a nice value so it'll work out for our calculations. So there's where we got our basic equations. Now what we want to do, we could do a variety of different things. We could do mesh analysis, but since I have a current source here, what's going to be easiest is to work through this using our node analysis. So in our case, I'll consider this first node, and what we've got is, we look at currents going in and currents going out, and the net of those has to be equal to 0. Now, I could just take it as this one as coming in and those going out, and take this one minus those, but I know this one's coming in, so I can also say that same exact rule as, whatever is coming in has to equal what's going out. So influx must equal outgo. So I'm going to say IS has to be equal to, that's what's coming in. We know it's coming in because the way it's oriented on the angles. And these coming out, well, this is going down to ground, it's pumping something up. This is where the supply is, that's got to be down. So I'm confident this is flow outs. If not, it would reverse for me automatically. Now the equation for a capacitor is its current is equal to j omega c times whatever the voltage drop is. In this case, the voltage drop across the capacitor is whatever Vs is. So I get j omega c times whatever my Vs. And that's the reactance of that capacitor. And then I also get a voltage drop from the resistor, except this one is Vs minus V out. That's what's dropping across the resistor. So then I could say that we have Vs minus V out over R. That is equal to the amount of current flowing through the resistor. So what comes in has to go out in the sum of these two ways. Now for the last node, there's nothing going as a income per se, and then we've got these two. I'm going to write the resistor as an outgo. I'll just say V out minus Vs all over to R. Now, since this is going to not actually be an outgo, it's going to be an incoming, Vs will be higher, so it'll be negative, so I'll end up with an influx. The inductor, I've got a voltage of V0 across it, and for inductors, it's just the voltage across it over J omega L. So that gives me my two basic equations that describe the steady state of this circuit. So I can now use the bottom equation to get an expression for my Vs. And all I'm going to do is take this minus Vs over R in here. I want to get Vs to the other side. Vs only appears in one spot. So what I'm going to do is multiply through by R. All right, so I'll get R times 0 is 0. R times this just goes away. And I just get R on top here. And then I just take the Vs to the other side, and I end up with Vs has to be equal to V0 plus V0 times R over J omega L. Now, if you notice, we get R over L. R over L is that classic time constant that you see all the time. Actually, L over R, but it's the time constant for our circuit when you're just dealing with a resistor inductor circuit. So you always find L over R, your time constant, or your base frequency, R over L. In any case, it's not too surprising you see the omega there, so you can see the time constant come out. I could also pull this in as one, pull the V0 out and have V0 times quantity 1 plus R over J omega L. But there's no real need for it, and I'm going to actually be solving over here for a sec, sticking this back in. So it's kind of more convenient to have it in this form, because what I'm looking for here is actually this one taken over, and so I'll just get that substituted up. In any case, let's do that one to simplify things up. I've done the bottom one. Now I'll take the very top equation, combine with this one, and we'll substitute in. So I get an IS, and then I still have this is equal to J omega C times Vs, but Vs is this. So, and this is, now I'm going to actually pull it out, 1 plus R over J omega L times V0. That's the first term, substituting in for the Vs. And then now I do the second term. Now the easiest way to get that second term, as I indicated just a few seconds ago, is if you consider taking V0 minus Vs over R to the other side. I'd have Vs minus V0 over R, which is this. That's got to be equal to this term right here. V0 R, or sorry, the R gets taken out. So I end up with V0 over J omega L. So I can replace this by V0 over J omega L. So that gives me my nice expression for I sub S. Now, if you notice, everything now involves just using my V0. Technically, what I really want is V0. Let me pull this in. We'll try to balance this up. So, if I just simplify a little bit, I've got IS equals, multiply through, I've got J omega C times the 1. Do a whole quantity of these. And the J omega, when I multiply J omega C times here, J omega cancels J omega. So I'll get RC over L. And then I've got this term here using V0. I'll pull V0 out of it as well. 1 over J omega L. This whole thing times V0. Now what I really want to do is have an expression for V0. So I can just divide. So I end up with V0 has to be equal to, and I've got my IS, whatever my source current is. We know what it is, but we'll just leave it generic at this moment. I could have also substituted numbers, but I think it's harder to follow at that point. So I've got my IS, and now we're going to take that and we're going to divide by, so we divide through, and I've got J omega c plus RC over L plus 1 over J omega C. Now, I'm going to connect these together and get a imaginary and real part. I've got IS, draw this more proper now. Put the real part first, RC over L, and then I've got plus J, the imaginary part, times, I've got an omega C here, and I can take the J up on top, which will just give me minus J, and pull the J out, so I have minus, and that gives me 1 over omega L. Now, I would like to be able to actually use this whole lovely thing to do some calculations here. In particular, the calculation I want to do is figuring out how big is V0. Now, again, I could put the numbers in first, but let's simplify this a bit. To write this easiest, particularly using phasors, we want to be able to have our expression involve the imaginary number come up on top. So the way we'll do it is we'll multiply top and bottom by the complex conjugate. Complex conjugate is I leave the real part alone and I just negate the imaginary part. And so therefore I'm going to multiply top and bottom. This is that old multiply by 1 trick. So I'm going to multiply top and bottom by RC over L minus J times omega C. Oh, please fit. Minus 1 over omega L. I hope this is readable. And same thing, top and bottom, RC over L minus J times omega C minus 1 over omega L. So same thing, top and bottom, that's therefore 1. What's going to happen is the RCL multiplies RCL. So on the bottom, I end up with RC over L squared. And I'll get RCL times this plus 1 and RCL times the minus 1. They'll be equal and opposite. They will cancel. And then I'll get this one times that. And I'll get J times minus J, which will just give me plus 1. I'll get plus. And then essentially what's inside squares itself. Multiplies by itself. So therefore it's squared. Omega C minus 1 over omega L. That quantity squared. And then on top, I just get the complex conjugate. RC over L minus J times omega C minus 1 over omega L whole quantity times IS. Okay. Now, we've got this great little expression here. There's not much more we can do with this, just leaving an expression, because right now it's actually pretty good shape. We have a nice solid expression of what's going on for each one. I suppose we could, calculate the numbers off this, but I think this is actually pretty clear. It's good for me. I've got my expression for V out in terms of it. I just have to stick in what my values are. So this is where we just remember what we had. I'll just pull this one over. We had picked omega to be equal to this. So that gives us our frequency. We hadn't actually picked a magnitude, so why don't we, I guess I should pick a magnitude, so we'll pick our IS to be equal to, let's say, how about 10 cosine 10 to the 4th t. So we'll just pick a voltage of 10 just to make life simple as it goes. So in addition, we've got R equals 10/11ths and some other fun stuff. So we have some components here we have to calculate. Let's calculate RC over L. Now RC over L, R is 10/11ths and C is 1.1 times 10 to the minus 3. And those are multiplied, and L was equal to 1 times 10 to the minus 4th. Okay, so obviously I picked this, so the 1.1 and the 1.1 here, right? 11 and 1.1. This will just end up being canceling out, because this goes on, and we will end up with just a straight 1. Okay? And then I've got 10 to the minus third over 10 to the fourth. So I will end up with 10. Right? So this just equals to 10. Because this is 1, in essence 1 over 1.1. 1.1, so we got 10 to the minus third over 10 to the minus fourth, which is just 10. Okay, so that's a nice clean expression, and then we've got omega c minus 1 over omega L. Okay, omega times c, omega is 10 to the fourth, and c is, right, times 1.1 times 10 to the minus 3 minus 1 over, and we've got 10 to the minus fourth times 10 to the fourth. All right, because that's omega and that's L. So this is just going to end up being equal to 1 on the bottom, so it's 1 over 1. So this whole thing goes to 1. And then we've got 10 to the fourth times 10 to the minus third, which gives us 10, times 1.1, so that's 11. 11 minus 1 means it is also equal to 10. All right. Grab another sheet of paper here. So now we just pick this one up and we simplify our expressions using what we have just calculated here. Let me make sure that's in view. So I'm just going to take these RC over L equals 10. That's right here. And we've got that V0 equals, and I've got a 10 minus J times something, and then our other RC over L is down here, which is 10 squared. And then I've got the omega c minus 1 over omega L, omega c minus 1 over omega L, that's also equal to 10. And we have that same expression down below, so another 10. And that whole thing times IS, and our IS we made equal to 10 angle 0 degrees. All right. So that's our 10 and cosine omega t. There's no phase angle we had stuck on it. All right, so looking at this, we've got lots of 10s throughout here. That was deliberate. So we've got a 10 on top on each of these. I can pull that out. I've got a 10 here. So on top, I've got a 100. I got a 10 squared, a 10 squared. Pull that out, that's 100 on the bottom. And then on top, I pulled the 10 out, so I still have 1 minus J. Pulled each of those out. I pulled the hundreds out on the bottom, so I still have 1 plus 1, so that gives me 2. And that is my magnitude, right? And this whole thing times 1, angle 0 degrees. And again, those cancel, just leave me 1. So I have this. Now, what I need to do is just find out what this one is in phasor notation. And multiplying two phasors, you multiply the magnitudes and add the angles. So this one, to figure it out, you need to get its absolute magnitude. Well, I've got 1/2 minus 1/2. So if you think of it, a lot of times we draw these as diagrams, and I think that might actually be helpful at this instant here to kind of figure this out. So if we treat this way, here's J. Evidently somebody made the mistake of calling me at this instant. So J, this is the imaginary, this is my real axis. So I go over 1/2, and then down 1/2. So that's this phasor. And I'm multiplying that by a 1 angle 0. Now, if you think about it, the angle of this one is 45. Now, 1 angle 0, that's just 1. I mean, the degrees are not going to change anything. So when I add it, it's not going to change anything. And the magnitude when I multiply it is 1, so it's not going to scale anything. So the only thing I'm going to end up with is this one's magnitude, this one's angle. So I end up literally just with this. And its magnitude is square root of 2 times a half. You can just see it's a half and a half. So half squared plus half squared, add together square root. And what that ends up giving you is the square root of 2 over 2. This is a very famous number to us. That is 0.707, blah, 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 blah. But it's approximately 0.707. And then the angle, as we said, it's minus 45 degrees. And I don't like that we use degrees, but it is what it is. Really, we should be using radians, which case we'd say this is minus pi over 4. Okay, so in the end, in book notation, we've got this. So given our input, this is what your output is. So if you want to write it, you could also take this out of phasor notation, and we could say that V0 is equal to 0.707 cosine of omega. In our case, omega is 10 to the 4th t minus, and I just can't write it their way. I have to put the radians here, otherwise I think people will make a mistake. Alright, so you just take the phase down and your magnitude down, and you are good to go. So this concludes your example for doing a second order system in steady state using phasors. Hope it helps. Good luck.